Settle in, you don't have to do anything from here. Let your body find the position it wants, nothing to correct. And let your eyes close whenever that feels easy. Take one slow breath in through the nose. And let it go all the way out. Again, in. And out a little longer than the in-breath. Now let the breath go back to its own rhythm. You don't need to manage it. We're going to move slowly down through the body, letting go as we go. Start at the very top of your head. Notice the scalp and let it soften. The forehead, let it be smooth and wide. The small muscles around your eyes, let them rest. The jaw, let the teeth come apart just slightly. The tongue, loosen the mouth. The throat soft. Now the shoulders, let them drop away from the ears. Feel the weight of your arms, upper arms, elbows, forearms. The hands, let the fingers uncurl and be heavy. Bring your attention to the chest, rising and falling on its own. And the belly, let it be soft, let it move. The whole length of the back, from the neck down. Let the back give its weight to whatever is holding you. The hips heavy. The thighs releasing. The knees, the calves. The ankles and then the feet. All the way to the toes, let them go. Now feel the whole body at once, head to feet, heavy, warm, supported. Nothing to hold up, nothing to stay awake for. In a moment, I'm going to start telling you a story about a small clay tablet and the people who made it. You don't need to follow it. You don't need to remember any of it. Just let the voice keep going, and let yourself drift whenever you're ready. There is a clay tablet, about the size of a hand, that sat in a museum in Istanbul for more than a century, without anyone particularly noticing it. It is not beautiful. It is a dull, biscuit-colored lump, slightly convex, the way a river stone is convex, with the marks of somebody's fingers still faintly visible along one edge where they press the clay into shape before writing on it. Across its face runs a diagram. Lines, some straight, some meeting at corners, enclosing shapes that a modern eye reads immediately as fields. And in and around those shapes, wedge-shaped marks pressed with the cut end of a reed, giving numbers. The tablet is called C.427. The S and the I stand for Sippar, the ancient city southwest of Baghdad, where it was dug out of the ground in the year 1894, by a French expedition led by a Dominican priest named Jean-Vincent Chale. Chale was a formidable scholar, the man who would later publish the Code of Hammurabi, and he dug at Sippar for a season and shipped crates of tablets back to what was then called the Imperial Museum of Constantinople. C.427 went into a drawer. It was catalogued. It was, in the narrow sense, known. But nobody had asked it the right question. The right question was asked, more than 120 years later, by a mathematician in Sydney who had been reading old excavation reports the way other people read novels. His name is Daniel Mansfield, and what he had noticed, buried in the records, was a reference to a field plan, a survey document, from a period that was not supposed to have produced field plans of that kind. Finding the actual object took him the better part of 2 years. The institution named, in the records, no longer existed under that name. He wrote to Turkish government ministries. He wrote to museums. Sometime in the middle of 2018, a photograph arrived in his inbox, and he found himself looking at a picture of a small brown tablet, and it took several more months of staring at it before he understood what he was looking at. What he was looking at was a property dispute, or rather, the geometry that a property dispute demanded. To understand why that matters, and why it is more interesting than it sounds, you have to sit for a while with the peculiar world that produced it. The old Babylonian period runs, in round numbers, from about 1900 to about 1600 before the Common Era. It is a strange and rich moment. It is the period of Hammurabi, of the great law codes, of a settled and literate bureaucracy along the Tigris and the Euphrates. And it is, crucially, the period in which land in Mesopotamia stopped being primarily the property of temples and palaces, and started, increasingly, being the property of individual people, who bought it and sold it and left it to their children. That change sounds administrative. It was actually mathematical. Because the moment a field belongs to a person rather than to a god, the question of exactly where that field ends becomes a question that can be argued about in court. And a court needs a number. Consider what it takes to answer that question in the year 1800 before the Common Era, standing in a flat, hot, alluvial plain with a rope and a wooden rod and no instruments of any kind that we would recognize. You have a piece of ground. Someone has sold half of it to someone else. You need to say how much land each party now holds, in a way that another surveyor, arriving later with another rope, will confirm. You need, in other words, a measurement that is not merely a guess. The Babylonians had a beautifully layered system for this, and it is worth walking through slowly, because the structure of the measuring system turns out to be the whole story. The smallest unit of length was the barleycorn, a grain of barley laid end to end, something like a 360th of a meter. 6 barleycorns made a finger. 30 fingers made a cubit, roughly half a meter, roughly the length of a forearm. 12 cubits made the unit that mattered most in the field, the ninda, sometimes called the rod, about 6 meters long. 10 ninda made a rope. 60 ninda made a length called the ush, 360 meters. And 30 of those made a biru, about 10 3/4 kilometers, which was less a distance than a measure of how far you could walk in a couple of hours. Notice what is happening in those numbers. 6, 30, 12, 10, 60, 30. These are not arbitrary. They are numbers chosen because they break apart cleanly. 60 is divisible by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. A system built on 60 is a system built for splitting things up, which is exactly what you need when the thing you are splitting is an inheritance among 3 sons, or a field between 2 owners, or a debt among a group of creditors. Area worked the same way, and here the language is lovely. The basic unit of area was the sar, which was 1 ninda squared, about 36 square meters, and the word for it also means garden. 100 sar made an iku, about 1/3 of a hectare, and the word iku means field. 6 iku made an esh. 3 esh, 18 iku, made a bur, which means something like a state. So the units of area were, in their names, the actual things being measured: a garden, a field, and a state. And underneath them ran a parallel logic in which land could be reckoned by how much seed it took to sow it, so that a measure of grain and a measure of ground were, in the mind of the person doing the reckoning, 2 aspects of the same fact. How big is this piece of land? It is a 2 barig field, meaning you would need 2 barig of barley to plant it. This is a very practical mathematics. It is not contemplative. Nobody is doing it for the beauty of it. And yet, out of it, something appears that looks startlingly like pure mathematics, and the argument about what exactly that something is has been running for 80 years and is not finished. Here is where the problem gets sharp. All of those area formulas, the ones that let you turn a field into a number of sar, assume that the field is a rectangle or can be cut into rectangles. If the corner is not a true right angle, the formula lies to you. It gives you a number that is too large, and it gives it to you confidently. 2 surveyors, each measuring the same slightly skewed plot, will get different answers, and both of them will believe their own answer, and now there is a lawsuit. So the surveyor's real problem is not measuring length. Length is easy. You have a rope. The surveyor's real problem is manufacturing a right angle in the middle of a muddy field. And there is a trick for this, and it is very old, and almost everyone has met it at some point without quite realizing what it was for. You take a rope. You mark it into 12 equal parts. You peg it down so that it forms a triangle with sides of 3 parts, 4 parts, and 5 parts. And the corner between the 3 and the 4 is exactly, not approximately, a right angle. It is exact because 9 plus 16 equals 25. The rope does the theorem for you. You do not have to know why it works. You only have to know that it does, and that it will still do it tomorrow, and that the surveyor from the next village will get the same corner. There is a word for the people who did this, borrowed from Egypt, where the same technique appears. Harpedonepti. Rope stretchers. It is one of the oldest professional titles in the world that describes a mathematical practice. What C.427 shows, and what nobody had a document proving before, is that old Babylonian surveyors were doing exactly this, in the field, with a legal purpose, and doing it with a precision that earlier surveys do not show. The tablet records a plot of land, part of which has been sold by a man whose name we have, Sin Belipli. It marks out the boundaries, including a section of marshy ground, which was worth recording because marsh and dry field are not worth the same, and a fair division has to account for that. It includes a threshing floor and a tower. And its corners are not approximations. They are built from Pythagorean triples. 3, 4, 5. 5, 12, 13. 8, 15, 17. That is more than 1,000 years before Pythagoras was born. It is arguably the oldest known example of applied geometry anywhere in the world. But the genuinely interesting part is not that they knew about right triangles. Several ancient cultures knew about right triangles. The interesting part is what happens when you try to use one. Because a triangle with sides 3, 4, and 5 is a specific size. Your field is not that size. You need to scale the triangle up or down to fit the ground in front of you, and scaling means multiplying. And in a sexagesimal system, multiplying is done by multiplying by reciprocals. To divide by 7, you multiply by 1/7. And here the base 60 system, so generous in most respects, turns cruel. 1/7 in base 60 does not terminate. It runs on forever, the way 1/3 runs on forever in our decimal notation. There is no exact answer. There is only a place where you decide to stop, and every place you decide to stop is a place where two surveyors can disagree. The numbers that behave in base 60 are the ones whose only prime factors are 2, 3, and 5. The Babylonians called these numbers regular, and every scribe knew them the way a musician knows scales. 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 16, 18, 20, 24, 25, 27, 30. These are the numbers you can divide by cleanly. These are the numbers that let you rescale. And so the surveyor's problem becomes a number theory problem, whether the surveyor wants it to or not. Which right triangles have sides you can actually divide by? 3, 4, and 5 are all regular, which is why that triple is the workhorse of the ancient world. But 5, 12, 13 has a 13 in it, and 13 is not regular. 8, 15, 17 has a 17 in it, and 17 is not regular. You can still use them, in the sense that you can lay them out, but you cannot freely rescale them, and that limitation is a real constraint on a working surveyor's day. Somebody at some point sat down and made a list. That list, or something very like it, is the second tablet in this story, and it is the most famous mathematical object to survive from the ancient world. It is called Plimpton 322, and it lives at Columbia University in New York. Its provenance is murkier than C.427s because it did not come out of a controlled excavation. It came through the hands of a dealer and adventurer named Edgar J. Banks, who is sometimes claimed, on thin evidence, as one of the inspirations for a certain fictional archaeologist with a hat and a whip. Banks said it came from Sankore, the site of ancient Larsa in southern Iraq. He sold it around 1922 to the publisher George Arthur Plimpton for what was reportedly $10. Plimpton, who collected the material of education, left it to Columbia in the mid-1930s, where it sat, again, quietly for about a decade. Physically it is small, about 13 centimeters wide, 9 tall, 2 thick. The handwriting dates it to around 1800, before the Common Era. And its left edge is broken off, which is a fact that will matter enormously, because the missing piece is precisely where the argument lies. What survives is a table. 4 columns, 15 rows. The rightmost column simply numbers the rows 1 through 15, which is a small detail that tells you the scribe thought of this as a list, an ordered thing, a document with rows. The two middle columns give, for each row, a number and a larger number. And when you check them, row after row, they turn out to be the short side and the diagonal of a right triangle whose sides are whole numbers. Pythagorean triples. Not the small famous ones either. The numbers get large. One row involves a triangle with sides in the neighborhood of 12,709 and 18,541. These are not numbers you stumble into. The leftmost surviving column is a ratio, and it decreases smoothly down the table, which is the detail that has driven everyone slightly mad for 80 years, because a smoothly decreasing ratio column in a table of right triangles looks, to a modern eye, exactly like a trigonometric table. The first serious reading came in 1945 from Otto Neugebauer and Abraham Sachs, who identified the Pythagorean triples and proposed that the scribe had generated them from pairs of numbers using a method equivalent to a formula we would now write with two variables. This was, for its time, a bombshell. It implied that Babylonian scribes were doing something that looked like number theory a millennium and a half before the Greeks. Then in the 1950s, Everett Bruins proposed something subtler and, in retrospect, more historically sensitive. He suggested that the tablet was not built from generating pairs at all, but from reciprocal pairs, which is to say from pairs of numbers that multiply to 1, both of which have terminating sexagesimal representations. This mattered because reciprocal pairs are not a modern reconstruction imposed on the tablet. They are demonstrably, overwhelmingly, what Babylonian scribes actually worked with. There are hundreds of tablets full of them. Reciprocal tables were the multiplication tables of Mesopotamian education. A child learning to be a scribe learned reciprocals the way a child today learns times tables. Bruin's idea was picked up and developed most fully by Alina Robson in a pair of papers around the turn of the millennium, one of which carries the wonderful title Neither Sherlock Holmes Nor Babylon. That title is a rebuke, and it is aimed at a whole style of scholarship. The Sherlock Holmes approach treats the tablet as a locked room mystery, a puzzle to be solved by pure cleverness, by whoever can find the modern formula that best reproduces the numbers. Robson's objection is that this method has no way of being wrong. Given 15 rows of numbers, a sufficiently ingenious person can always find some formula that generates them. The formula's existence proves nothing about what the scribe was thinking. It proves only that the mathematician who found it is clever. Her alternative is to ask what else we know about this scribe's world. What other tablets did people at Larsa, around 1800, write? What words did they use? What problems did they set their students? And when you look at the tablet through that lens, several things line up. The column headings, when read as Akkadian rather than as mathematics, use vocabulary that belongs to the world of cut and paste geometry, the technique in which a scribe solves what we would call a quadratic equation by literally imagining a square being cut apart and rearranged, completing the square in an almost carpentry sense. The numbers involved are exactly the kind you would use to set a student a problem that comes out neatly. And tellingly, the tablet contains errors. At least 6 of them, wrong values that scholars have identified, and mostly agreed on the correction for. That last point is a quiet but heavy piece of evidence. A table of exact mathematical truth with 6 mistakes in it is not a reference work. It is somebody's working document. Robson's conclusion is that the author was most likely a teacher, generating a set of problems that would have tidy answers so that the students could be tested and the answers checked. Not a mathematician discovering number theory. A person at a desk making tomorrow's homework. That would probably have settled into the consensus, and largely did, if not for 2017, when Daniel Mansfield, with his colleague Norman Wildberger, published a paper arguing that Plimpton 322 was a trigonometric table, and moreover a better one than ours. Exact, they argued, where ours are approximate, because it uses ratios rather than angles and never needs to round anything off. The press coverage was enormous and used words like superior. The response from historians of mathematics was swift and was not gentle. Evelyn Lamb, writing in Scientific American, pointed out that the trigonometric relationships in the tablet had been recognized since the 1940s, and that the real question, the interesting question, was never whether they were there, but what the tablet was for. Others noted the awkwardness of calling something exact when it contains 6 errors. And the deeper objection was Robson's methodological one, restated, that reading a modern structure into an ancient artifact and then admiring the ancients for having anticipated us is a way of finding ourselves in the past rather than finding the past. What happened next is, to my mind, the most admirable turn in the whole story, and it is the part that never gets into the headlines. Mansfield kept working. He went looking, in the excavation records, for evidence about what old Babylonian surveyors actually did, which is how he found C.427 in the first place. And in 2021, he published a second paper on Plimpton 322, with a much quieter title, A Study of Rectangles. The argument had changed. It was no longer that the tablet was a trigonometric table. It was that the tablet is a systematic investigation of a question that a surveyor would care about intensely. Which right triangles have sides and diagonals that are regular numbers, and can therefore be rescaled freely. Read this way, the tablet is not abstract number theory, and it is not trigonometry. It is a catalog of usable shapes. It is the answer to the question that C.427 raises. A surveyor confronting a field needs a right angle at a particular scale, and only certain triples will let him get there without an infinite sexagesimal expansion. So somebody worked out which ones and wrote them down, and the fact that the list is ordered and that the ratio column decreases smoothly is a consequence of organizing the search, not evidence of trigonometry. There is a supporting piece of evidence for this that I find genuinely charming. Another tablet, catalogued as MS3971, contains a problem that asks the student to find a rectangle with a diagonal of 7, using only rectangles that have regular diagonals. 7, remember, is not regular. It is the awkward number. The problem is essentially asking a student to work around exactly the difficulty that the whole system creates, and it presupposes that the student has access to a stock of known regular rectangles to work from. Which is to say, it presupposes a list. Something like Plimpton 322. None of this is settled. Robson's caution still stands, and it applies to Mansfield's second reading as much as his first. But something has shifted, and the shift is that the debate is no longer about which modern formula the Babylonians had secretly discovered. It is about what problem they were trying to solve, which is a much better question, and one that the mud and the ropes and the property lawsuits are better evidence for than any elegant formula could be. I want to end by sitting with what the whole thing implies, because I think it is quietly enormous. We tell the story of geometry as a Greek story, and in that story geometry begins in contemplation. Thales looking at shadows. Pythagoras and his followers finding number in music and in the heavens. Euclid deducing the world from 5 postulates. Geometry, in that telling, is what happens when people have leisure and turn their minds to eternal things, and its connection to the physical world is almost embarrassing, a descent from the perfect circle to the drawn one. The Mesopotamian evidence tells a different story, and the 2 tablets together tell it clearly. Here, the right angle is not contemplated. It is manufactured with a rope because 2 men are arguing about a boundary, and a scribe has to write down a number that will hold up. The theorem that we name after a Greek mystic appears here as a piece of equipment, in the same category as the measuring rod and the reed stylus. The deep number theory, the study of which integers factor into 2s and 3s and 5s, arises because a working surveyor kept running into fractions that would not close, and somebody got tired of it and made a list. And the Greek route, the astronomical one, produced trigonometry as we have it, built on angles and on chords in a circle, because the sky is a sphere and you are measuring across it. The Mesopotamian route produced something else, built on ratios of sides in a rectangle, because the ground is flat and you are pacing across it. Two different geometries, growing from two different practical needs, and one of them became the one we all learned in school, and the other became a puzzle for specialists. There is one more thing, and it is the thing that keeps the argument permanently open. These tablets do not explain themselves. There is no prose on Plimpton 322 saying what it is for. There is no note on C.427 saying here is why I chose these triangles. The scribes were writing for other people who already knew, for colleagues who shared a training so complete that stating the purpose would have been as odd as writing down what a chair is for. Everything that was obvious went unrecorded. What survives is the residue, the numbers, the marks in the clay, and the enormous silent context in which they made sense has evaporated. Which means that every reading of these tablets is, in part, a reconstruction of a world. Not a decoding. A reconstruction. And the disagreement between a teacher setting homework and a surveyor cataloging usable shapes is not really a disagreement about arithmetic at all. It is a disagreement about who was in the room. The clay does not say. It has held its numbers for 3,700 years, patiently, through a fire that hardened it, through the collapse of the city that made it, through the drawer in Istanbul and the shelf at Columbia. And it is still holding them now, in the dark, in a case somewhere, waiting for somebody with a rope to come and ask again.